All right, let's talk about what I believe is the last section of chapter 8, which is section 3. Now, there is a section 4. I just haven't decided yet if I want to go down that road or not yet. But we'll see. We'll see. So for now, we'll think 8.3 is probably the end. And 8.3, the way this chapter is kind of worked is it actually gets sort of easier from beginning to end. Because we've learned all these little tricks that make the problem so easy now, but we didn't have those tricks at the beginning of the chapter, but now we do at the end of the chapter. So it's really not too difficult to do mathematically, with our calculator. It's very straightforward. Understanding it's one other thing, though. I hope I can do the best I can to make you understand what the reason behind all this stuff is. But anyway, we'll go ahead and get started. So state vectors, okay? Since Markov chains are a stochastic process, or are stochastic processes, we do not ordinarily know what will happen at each stage, and we must describe them in terms of probabilities. So a state vector is as such. Consider a Markov chain with n states. So let's say our chain, for example, has 3 states. And by states, I mean conditions it can be in. So, for example, we did one earlier where we talked about a person being employed or unemployed. That person is in one of 2 states, the 2 states being employed or unemployed. One with 3 states could be maybe regional, like maybe you're a taxi driver and you're either in uptown, downtown, or midtown, right? There's 3 different places you could be, or 3 states, so to speak, you can be in. So let's consider something, n states. So n can be it could be 4, 5, 6, whatever, however many states are in our problem. But let's consider an example of 3 for a minute. A state vector for the Markov chain is the probability n vectors, x equals x1, x2, all the way to xn. So what this means is that these are probabilities for each state. So x1 would be the probability of being in state 1, x2 would be the probability of being in state 2, and you would have that go on for as long as you had, as many states as you had. So if we only had 3 states, then I would have a probability x1, x2, and x3. Those are just representing the probability of being in state 1, probability of being in state 2, or probability of being in state 3. And we call this a state vector. So in long story short, a state vector is just a way to tell us the probability that we exist in a certain state right now. So let's look at an example, sort of explain an example of a state vector, kind of how it would be used. So let's look at the Metroburg Heating and Air Conditioning Company that we talked about in section 8.1 that has 3 states. Now this was about a dispatcher, and the dispatcher sends out trucks to different jobs for this heating and air conditioning company. And the probability that there's one driver who's been keeping up with where he's been going has come up with these probabilities that he could, 0.7, 0, and 3 as a state vector is what he's determined. So what that means is that there's a 0.7 probability, or 70% chance, that this driver is in, I believe it was east. I think it was east, central, and west was how this was broken up. East being 1, central being 2, and west being 3. So 0.7, the first one, is a 0.7% or 0.7 probability, or 70% chance that our driver is in the East District. 0, telling us that he is not in Central District, because the probability of 0 means he's not there, right? There's no chance that he's in the Central District. And then 0.3 tells us that there's a 0.3 probability, or 30% chance, that our driver is in the West District. So this state vector, 0.7, 0, 3, is just the probability of our driver being in a certain state. State 1, state 2, state 3, or the east, central, and west state. Now, if the system is known to be in a specific state, meaning I know, for example, I know that my driver is in the East District, then there's a 100% chance, or one probability of 1, that he's in the East District, because I know for a fact that he's there, which means I know he's not in Central and I know he's not in West, which that's what makes the state vector 1, 0, 0. That state vector is telling me that it's 100% certain he's in East. There's no chance he's in Central or West, because I know for a fact that he's in East. Okay. So again, it's a probability thing. What's the probability or likelihood that our driver is in a certain state? But if we know he's there, then that probability is 1. That's guaranteed, right? So more about state vectors. The initial state of the system is denoted by x0. So x0, this is just notation. x0 is just the way we would indicate our initial state. So the 0.703 that we just talked about, that's our initial state, where we could be like right now. After one transition, the state vector will be called x1. So x1 represents the probability of being in different states after one transition. x2 would be the probability of each state after 2 transitions, and so on if you do x3, x4, and whatever. It's just a way of keeping track of the probability of each state through different transitions. Now, here's our theorem on state vectors. It's a very simple formula, okay? So I know it looks weird because it's got like x's and k's and stuff, but it's the notation is weird, but the meaning behind it's rather simple. So xk is representing the vector, the state vector after k transition. So basically, it's the probability of being in each state after however many transitions. So k represents, 2, 3, 4. If you're talking about 2 transitions, 3 transitions, 4 transitions, or whatever. So it's basically the answer. It's the probability of our states after a certain number of transitions. x0 we already talked about being the initial state vector, kind of where we're at in the beginning. And then p to the k power, this talks about what we did in 8.2, which is our transition matrix after a certain number of states. So remember, k represents however many states or however many transitions we're going through. So for example, if we did p to the 3rd power, it would be our transition matrix to the 3rd power, which is finding the transition matrix after 3 transitions. So let's kind of jump into an example and we'll see how these all really play out. So Markov chain model for the Metroburg Heating and Cooling Company has this transition matrix. I believe it's the same transition matrix that we did in section 8.1 or 8.2. I don't remember which one, but it should be the same matrix we saw earlier in a previous video. If the initial state vector is 0.7, 0, and 0.3, find the state vector after one transition. So if you remember the formula we just talked about, again, it seems complicated, but it's very, very easy to use. This right here, the xk, is going to be our answer. So we're trying to figure out what the state vector is after one transition, right? So k is going to represent 1, since k represents the number of transitions. x0 is what we already know. We already know x0 is this state vector here. So if I'm just plugging these in, I know that my answer is going to equal this state vector, 0.7, 0, 0.3, times p to the k power. Now, p is my transition matrix. I already have that transition matrix here, 0.5, 0.4, 0.1, 0.1, 0.6, 0.3, 0.3, 0.6, 0.1. To the k power. So remember, we're talking about one transition, so this to the 1st power. And it's as simple as just kind of typing this in now to our calculator and getting our answer, and then let's explain the answer once we've done that. So let me close this. I'll go ahead and keep that on the screen for now. But we're going to go to our calculator. We're going to type in our matrices. So remember, second and that key gets us our matrix menu. We're going to go to edit, and we're going to put in a 3 by 3 Well, actually, let's do the 1 by 3 matrix first, right? The state vector, 1 by 3. So this will be the 0.7, 0, and 0.3 matrix. And then I'll put in another matrix, which is my transition matrix, that 3 by 3 one. I'll put that in as B here. So 3 by 3. And that one, let me move this over so I can see it. 0.5, 0.4, 0.1. I'll just go ahead and type it in without talking. Oh, crap. Okay. So my matrices are in the calculator. So now all we're going to do is just multiply them together like you see on the screen. We're going to do the vector by the transition matrix. So the 1 by 3 first and then the 3 by 3 second. So we're going to go to our matrix menu. We're going to choose the 1 by 3. We're going to multiply it with the 3 by 3 and have the calculator do all the work for us. And we get 0.44, 0.46, and 0.1. So we get 0.44, 0.46, and 0.1 as our answer. So what this means is that after one transition, there's a 44% chance of being in state 1, which is the East District. There's a 46% chance of being in state 2, which is the Central District. And there's a 10% chance of being in the West District. So it tells us the probability of being in a certain state after a certain period of time. So let's try this again, but let's look at this example because it's it gives you all the information, but you kind of have to dig a little bit into the problem to understand how to use this and get the answer. So example 2, a Markov chain has a transition matrix P as shown there. If the system begins in state 2, find the state vector after 2 transitions. So again, we're using the same formula, xk equals x0 and then p to the k power. Now k in this case is 2 because we're looking after 2 transitions. So this will be my answer after 2 transitions. This is what x2 represents my final answer. x0, now that's what we need to know. We know that p is this matrix here. So 0.5, 0.5, 0.8, 0.2. K power, so that'll be to the second power since we're looking at 2 transitions. But what is x0? We need that information if we're going to find our answer. Because in the last problem, our state vector was 0.7, 0, 0.3. But it doesn't really give me a state vector here. It kind of does, though. It secretly does. It says if the system begins in state 2. So what this tells me here is that I know for a fact that I am guaranteed I am starting in state 2. Now, since this is a 2 by 2 matrix, my state vector is going to be a 1 by 2 because there's only 2 states. If it's a 2 by 2 matrix, there's only 2 states. Now, if I know that I'm in state 2 to begin with, I know it's a 0% chance I'm in state 1 and a 100% chance or probability of 1, a guarantee that I'm in state 2. So that's what kind of this was talking about earlier. If I know I'm in a certain state, then it's a 1 for that state and 0 for the others. Well, I know I'm in state 2 because the problem tells me I'm starting in state 2. So I know it's a 1 for state 2, which means a 0 for state 1. So this is my state vector. This is what I'm going to use as my x0, and I'm going to multiply it with my transition matrix there. So it's sort of subtle, but it does give you the information to create this vector. So now we just type it in the calculator and let the calculator do its thing. So we're going to go back to our matrix menu. We're going to edit our matrices. I'm going to make this a 1 by 2 matrix. 0 because I know I'm not in state 1, and then 1 because I know I'm in state 2. Then we're going to go back. We're going to put in our 2 by 2 matrix. So this was 0.5, 0.5. Oops, apparently I didn't like that. 0.5, enter, 0.5, enter, 0.8, and 0.2. All right, So now we just need to multiply them together. So actually, instead of typing it all back in again, let me, oh, well, yeah, let me just copy that. Hit enter on that again. It should be good. 0.8.2. That seems weird. That's got to be right, though. Yeah. So we took our matrix A, right? I'm just going to double check, times our matrix B. We ended up with that 0.8.2. Yeah, okay, cool. So our answer is 0.8.2, which this means after 2 transitions, there is an 80% chance that I'm in state 1, a 20% chance that I'm in state 2. All right. Now this is just real quick. Basically, a Markov chain is said to be regular if there is a positive integer k such that p to k has all positive entries. So basically, if we can find any transition where all the entries are positive, then our transition matrix is P. It doesn't have to be the first one, doesn't have to be the second one or the third one, but if there's any of them that are, so it could be the fourth one, but none of the others, then this will be considered a regular Markov chain. But if every matrix, basically, if every matrix that I've raised to power, so if I P to the first, P to the second, P to the third, P to the fourth, and every single one after that, if none of them have all positive entries, then it's not regular. But if just one of them has all positive entries and the others don't, it's considered to be regular. So the key to this is kind of finding patterns. But let's look at our example here. So I've got 2 different ones. We'll call this the first one, and we'll call this the second one. They're 2 different problems. To see if this is regular, we're just going to take it, raise it to some powers, and see if we notice anything. So this is 1/2, 1/2, 1 and 0, which I'm just going to put in as 0.5, 0.5, 1 and 0. So go back to our matrix menu. I'm going to go ahead and type this in as a 2x2, 0.5, 0.5, 1, 0. And I'm just going to take that matrix and raise it to a couple powers. So second power. Now already you notice that just taking it to the second power, I have every entry being positive, 0.75, 0.25, 0.5, and 0.5. They're all positive numbers. They're all bigger than 0. So that tells me that this matrix is regular. We're good there. Now let's check this one. So let me go back to my matrix menu, and we'll type it in. So that matrix was 0, 1, 1, 0. So 0, 1, 1, 0. All right. So let's test it out. Let's take that matrix and let's raise it to the second power. And we get 1, 0, 0, 1. Now this is not regular right now, because it has to have all positive entries, which means basically it can't be 0. 0 is not a positive number. 0 is a neutral number. So if 0 is in it at all, then it doesn't count. It has to be positive. It has to be bigger than 0. Okay, 0.1s, 0.2s, things like that. You can't have 0 in the matrix. So far we have no luck. Not a regular one yet. So let's try taking that matrix and doing it to the third power. Now doing it to the third power, we get 0, 1, 1, 0, which is exactly what we started with. Again, we have zeros in the matrix, so it's not regular. All 4 values would have to be positive. And if we do just one more time, so go to the fourth power, you'll see there's a pattern here, right? It keeps going back and forth between 1, 0, 0, 1 and 0, 1, 1, 0. So no matter what power I raise it to, it's always going to be just 1s and 0s. So that tells me that there's I can do this all day long to any power I want, but I know that it's never going to have a matrix that doesn't have any 0s in it, so it's not going to be regular. That makes some sense. All right. So Markov chain has a transition matrix as shown, for which state I is pi3 largest, for which state I is its smallest. This is just, again, another one of those, do you understand the notation type of questions? So I represents, it could be the first state, the second state, or the third state. In this case, because we have a 3x3, so we have 3 states. So I can be 1, 2, or 3. So if I think, let's call state I state 1, for example, right? Then I'd be looking for P13, which P13 would be this number here, right? If I was 2, then this would be P23, which is this number here. And if I is 3, I'd be talking about the state 33, which is this number here. So the 3 means basically the third column, and then I means the first, second, or third row for that column. So it's basically just this third column here is what we're focused on. So it says for which state I is at the smallest. So we're just to answer this, we're talking about, because there's no parenthesis next to this, we're talking about the original matrix, the original transition matrix that we see on the screen already. So for which state I is at the smallest? Well, the first state and the third state are both at 0, so they're the smallest. So to answer number 1, state 1 and 3 are smallest because they're both 0. And when it asks what's the largest, well, largest would be state 2. State 2 is largest because it's 0.5, and 0.5 is the largest one. So now we're just going to answer the rest of these questions. So this is asking after 2 transitions. So what we need to do is take this matrix to the second power and then look at those rows, or that third column again, to see which one's the biggest and which one's the smallest. And we need to do that to the third power as well for the last part of this question. So we just go to our calculator and we would just type in this matrix. We're going to make it a 3x3 0.5, 0.5, 0, 0, 0.5, 0.5, and 0.75, 0.25, 0. Right, we're just going to take this matrix and go to the second power with it. And so again, we're looking at the last column. So the 0.25, the 0.25, and the 0.125. So to answer the question for part 2, which is the largest and which is the smallest? Well, state 1 and state 2 would be tied for the largest because they're both 0.25. And then state 3 would be the smallest because it's 0.125. And again, we're looking at the third column on that. And then one more time, let's take this matrix. Can I make this bigger? Yes, that's helpful. All right, let's take this matrix and raise it to the third power to answer the last part of our question. So which state is the largest? Which state is smallest? Well, the largest would be the first and the third because they're both 0.125. Or I'm sorry, they're 0.25. And the second state is the smallest at 0.1875. So that's just, again, kind of making sure you understand how to read this notation because it will be useful later on. All right. Now this example is already completely done for us. And I did that for a reason because I just want to notice the pattern. I don't want to take too long to work it out. So consider the transition matrix that we see here, the 0.5, 0.4, 0.1. I believe, again, this goes back to the heating and air conditioning company. I think that's the same matrix we saw in that example. And now look what happens when you raise it to a certain power, right? If you raise it to the second power, you see 0.32, 0.20, 0.24, right? None of these really seem to match. 0.5, 0.58, 0.54. Those are pretty close. 0.18, 0.22, 0.22, those are pretty close, right? If you take it to the fourth power, after 4 transitions, notice the 0.2456, the 0.2328, the 0.2376. These numbers are very close together. So are the values in the second row, or second column rather. Those are also really close together. And then the third column, these are also really close together. And if you take it, let's say, to the 8th power, right, 8 transitions, you'll notice that these values are almost exactly the same all the way through. So this is considered to be something rather interesting, something known as the stable vector. So a stable vector is basically the vector that our probabilities all approach, that our transition matrices will always approach, but it only happens after a usually significantly large number of transitions, like 8. 8 transitions, that's a lot. So that's why you see after 8, that was all those values being very close. But imagine like after 20 transitions, right? After 30 transitions, they'll basically be the exact same number. So our goal is to figure out what is the stable vector for our matrices. What's the probability going to be for state 1, state 2, state 3 in the long run? So obtaining stable probabilities is actually really easy. There's a formula for it using systems of equations that we can do. I'll show you that, but that's not really how I'm going to answer it, because I know basically, as we just saw, if I take my matrix and raise it to a really, really large power, I will get to that stable vector. Which, by the way, when I say stable vector, when I'm talking about, I don't know if it mentions it here. It doesn't really mention it here. But I'm talking about how every row is essentially the same row. The first row is pretty much identical to the second row, which is pretty much identical to the third row. What are the values of these vectors that's considered my stable vector? So my stable vector in this problem would basically probably be the 0.2369, 0.5526, and 0.2105. That would, when I ask what's the stable vector for this problem, it's going to be this, because that's essentially what all the matrices are approaching. Okay, but we're going to do it with fractions, and that's not going to be too big a deal. Our calculator can tell us the fractions.